now turn on. Okay, the recording is going.
So thank you very much. Yeah, okay, so this is now part 3. And welcome back. We are now in the position really to cook up a couple of new topologies on the symmetric algebra of a locally convex space. And just to recall our framework, the reasoning, so what we want to do is we want to investigate a Poisson structure on a vector space, and we want to investigate it on the polynomials on that vector space. And so in order to keep things easier in view of possible infinite dimensional applications, we start with the vector space V and think of the polynomials on the dual, which is complicated, but we model them as sort of a tiny little subspace of the polynomials, being the symmetric algebra over V itself. In finite dimensions, this is the same thing. Yeah? But in infinite dimensions, this is a much smaller space, but it will be manageable. And a constant Poisson structure is then encoded by a bilinear pairing on the vector space. And out of this, we build these operators P lambda, sort of extending this as a biderivation on 2 copies of the symmetric algebra. And in finite dimensions, using a basis, you can view this really as a Poisson structure with constant coefficients. And then we were able to write down this Poisson bracket. So we only need the antisymmetric part of the lambda of this bilinear form, and we still had to multiply together the 2 factors. Yeah? And the nice thing is, having this P lambda, one can directly write down a star product for that. The Poisson structure only depended on the antisymmetric part of lambda. The star product really depends on lambda and the symmetric part as well. Yeah, you see from the formula. And so it's not completely obvious, but it's a nice little exercise. You can do it in a more or in a less clever way to check that this is associative. Yeah? And then we had a general strategy how to pursue convergence. Yeah, so the first part was in green. Yeah, was a big piece of hope that we find a subalgebra where convergence is sort of trivially guaranteed. Yeah, and here, wow, yeah, it is true. Yeah, this star product on the polynomials, of course, it converges in H bar. Yeah, it's simply a finite series. Yeah, it's a finite sum always. Yeah, because we have A and B are symmetric tensors. They have a maximal degree, and the P lambda lowers the degree in every step. After finitely many, we are down to 0. Yeah, so this star product for a fixed A and B has only finite number of terms. Convergence is no problem. Yeah, so the second part, and this is where we stopped yesterday, was really now to say, well, polynomials are still a bit boring. Yeah, we want to go beyond polynomials. So the idea was to cook up a topology, a locally convex topology on this algebra, which is hopefully pretty coarse, yeah, so that its completion becomes large and contains then interesting transcendental functions, not only the polynomials, much more than the symmetric algebra. But in order to make sense, the star product should be continuous for this topology, so that it extends to the completion, yeah, by general nonsense. Yeah? So this is the part where we also need a bit of hope to find such a topology. And so you would now say, well, then take the course's topology such that blah, 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 do some universal construction. However, this is not so easy. Locally convex topologies with extreme properties, you have a couple of universal constructions, but they usually refer to linear things. Yeah, so you can say, well, take the coarsest topology such that this linear map becomes continuous, or take the finest topology such that that linear map becomes continuous. But our product is bilinear, and it goes to the same space back. That makes it very bad. Yeah. So if we would have fixed the topology on the target already, we could ask for the coarsest topology such that the thing is continuous. But we don't have the topology on the target yet. We search it also for the target and the source simultaneously. That makes it difficult to have such a kind of a universal extreme property locally convex topology. Yeah? So we have to cook up something by hand. Yeah? And in fact, one can show that there are many choices and other possibilities. Yeah? So it's hard to characterize what we do here, in which sense it is optimal. Yeah? This is not so easy, actually. So now we have to cook up this topology. And to that, I view these symmetric tensor powers as being symmetric tensors in the all tensors, and use this pi topology on fixed tensor degrees. Yeah, and that was this tensor product of seminorms and also a k-fold tensor product of seminorms that defines the pi topology on this k-fold tensor product of V with itself, and we take the subspace topology as usual. But the problem was we don't have tensors with fixed degrees only. This is easy, yeah, but we have a direct sum of all of them. Yeah, and now we have to cook up a topology on this direct sum. And there you know, maybe you don't, but there are two canonical topologies known. One is the Cartesian product topology. This is way too coarse to be of any interest. And the other is the direct sum, the locally convex direct sum topology. This is way too fine to be of any interest. In particular, we would not get any interesting completion anymore. Yeah. So for finite dimensional vector spaces V, this would be already complete. So we would not have gained anything. Yeah. So the idea is, well, we would like to have something in between. Yeah. And the suggestion, and that was where I stopped last time, was, well, now the plumbering sort of starts. Yeah. We have to invent something. So the idea was we fix a parameter R. This will be a parameter of the whole game. And then out of a seminorm on V, we can cook up a new seminorm on the tensor algebra, yeah, by taking its tensor powers, pk, yeah, which we can apply to k-fold tensors. Yeah? And then we want the summability of these numbers. Yeah? And the summability property has to be compared to the growth of k factorial to the power r. Yeah? So we sort of, depending on R, we want these numbers here, the pk of the coefficients vk, to decrease fast enough, yeah, so that this quantity becomes finite. Yeah, that's sort of the idea. Well, as long as we are on the tensor algebra, this is finite because the sum is finite. But concerning completion, this will be then a summability condition. Yeah? And now what we do is we take all continuous seminorms on our vector space and perform this construction. So we get a whole bunch of seminorms PR for fixed R, but varying P. And all those together define what we call the TR topology on the tensor algebra. And this will be then the SR topology on the symmetric algebra, which is simply the subspace topology. Yeah? So that's the subspace topology. Okay, so now I should give you a couple of properties. Yeah, I mean, what is this construction good for, and why taking a sum here and not something else? And so the first observation, maybe, well, it's some. Well, this is some. What is better to read, the bigger pen or the smaller? I don't know. Maybe go back to this one. Some features, yeah, of this construction. Yeah? So if we have two seminorms P less than Q, then it have an estimate between two seminorms. Well, that's easy to see. Then PR is dominated by the corresponding QR. That's easy to see. I mean, don't have to say anything important here. Then the funny thing is, on the other hand, I mean, if we have an estimate involving a multiple, let's say doing something like 2 times p and forming this guy here. So k to sum of t infinity, k factorial to the power r. And then we have to do the k-fold tensor power here of the kth component. So what is that, for example? Well, we get here k to infinity r. And then, well, it requires a little bit of thought that we just get out this factor here. Yeah. And then we have pk, vk like that. So, of course, pr of v is smaller than that. This follows by the first part. But on the vector space v, the seminorm p and twice the seminorm p, they are sort of equivalent. I can estimate one by the other. I can estimate 2 times p by 2 times p. Yeah, that's but this is no longer true here for those. Yeah, this cannot be estimated by PR anymore. Yeah, this additional growth of 2k here cannot be taken out of the sum as a constant. Yeah, this grows above all bounds. Yeah, and so you see that even if you start sort of with a normed space, yeah, you get all multiples of the norm. They are continuous, and they will produce such factors here. Yeah, and so in the end, this topology will not be normable anymore. Yeah, this on the tensor algebra. Yeah, so you really go beyond normed stuff. Yeah, in this construction. Yeah, this is sort of the feature 2. Yeah, so we have to, and of course, taking prefactor 2 is not important here. Yeah, I mean, it can be done with any constant. Yeah, so that is this one, and maybe another way to do that is why taking the sum of all these coefficients. You could do maybe the following would be an alternative. You take the sup, for example, of all these numbers, k factorial, the sup over k factorial to r pk of vk. Yeah? This would be also a seminorm on there. Yeah? Or you can take an sort of a LP kind of summation. Yeah, so not this what we do here is kind of an L1 type thing. Now we do an L infinity, which is a subnorm, but you can do all kind of LPs in between. Yeah, and of course the sup is smaller than the sum. Yeah, that's easy. Yeah. So you have you for sure have this equation. Yeah, this is easy. Yeah, but and the funny thing is that you do not get a different topology. Yeah, in general, subnorms and L1 norms are different topologies, right? But because we have these prefactors all in the game by definition, yeah, we can also estimate the PR again by a P, and we take 2 of them. I think 2 is enough, right? And take the subnorm over those, and then we need a prefactor. Yeah. So it was not really a choice. Yeah. The taking the sum, we could have taken the sup also, would lead to the same topology. Yeah. We have so this to same TR topology. Yeah. If we take all again, yeah, that's the crucial point. We need all of them, yeah, to get. We are allowed to take all continuous seminorms, and then if P is a continuous seminorm, 2 times P is a continuous seminorm as well. So it's part of the game. So we can have mutual estimates, and therefore the topologies agree. Yeah, so that's sometimes convenient. Yeah. For technical estimates, sometimes it's easier to estimate a sup. Sometimes it's easier to use a summation. Yeah, and yeah, then of course important is that if we restrict this now to a fixed subspace of fixed tensor degree, our seminorm. Well, what is that? Well, that's easy from the definition. It's k factorial to the power n and the k-fold tensor power of the seminorm. This is just a number. And so we reproduce the seminorms of the projective topology. So the conclusion is the subspace topology inherited by the kth tensor power inside this TV is just the usual original pi topology. So in other words, the projection onto the kth tensor power and the inclusion back into here, they are continuous. And this is an embedding here even, yeah? This is an embedding. Yeah, the induced topology is the same. So on each fixed degree, this is all fine, and it doesn't even depend on R. Yeah, I mean this is true for all prefactors. Yeah, I mean on a fixed tensor degree, this is just a number. Yeah, it's only the important thing is how things vary with increasing degree. Yeah, so now the first nice thing is we have a product. The tensor algebra is an algebra after all. Yeah? We have the tensor product. So now let's estimate this for some elements in the tensor algebra. Yeah? And if you do that, well, you get the following quite funny formula, which is sort of optimal. Yeah? I mean, you get 2 to the power r times p, and then you have to do this thing, this whole summation, and 2 to the power r of q, p again, sorry, of w. Yeah? And instead of 2, you can use any number bigger than 1. Yeah, but you need a number bigger than 1 here. Yeah, it's not possible with 1. Yeah, so that means 2 things. Yeah, so and I maybe I should take r bigger than 0. I don't know if this is true for r less than 0. Maybe not. I don't care. We are interested in r bigger than 0 anyway. So what does that mean? Yeah, the tensor product on the tensor algebra, which makes this the universal algebra generated by V, is continuous for the TR topology. That's this estimate, yeah. And for r equals 0, something special happens, yeah. For r equals 0, this thing here will be just the same seminorm as on the left-hand side. Such algebras are called locally multiplicatively convex. Then the seminorms are submultiplicative. This is not true for r positive. Yeah? It's only true for r equals 0. Yeah? Yeah, maybe for negative, it's also true. Yeah. You that's true. Yeah, but for this TR of V is locally multiplicatively convex algebra. Yeah? But for the others not, for the positive ones not. That's the important point. Yeah? And as I said, locally multiplicatively convex algebras are those where you have a defining system of seminorms which is submultiplicative. Yeah? This. It's not, no, it's still a very interesting non-trivial algebra. It's the free locally multiplicatively convex algebra generated by V. And in order to have such a thing, you really have to prove something, that there is a free algebra in this category of LMC algebras. Without LMC, there is no free locally convex algebra generated by a vector space. That's the bad thing. Otherwise, life would be so much easier, yeah? Because then if you would have a free locally convex algebra generated by a vector space, then you could impose on any algebra for any sort of multiplication a locally convex topology such that it becomes continuous just by taking the quotient of the free one. Yeah, but there is no free one in general, only for the LMC algebras, and that's it. Yes, yes, in universal property. Yeah, so. Sorry, yeah. The question was whether this what was the question? Yeah, what kind of algebra do we get for R equals 0? We will determine that. Yeah, for the symmetric algebra, I can write down the thing later on. For the tensor algebra, this is the tensor algebra with a certain topology, and this for R equals 0. This is the I should write it here. This is the free LMC algebra generated by V, and therefore it's clear what it is. It is by a universal property. Yeah, it's and up to isomorphism. This is a unique isomorphism. This is fixed. Yeah, this universal property fixes it. Yeah, so the problem is for all what we do in quantization theory, locally multiplicatively convex algebras are the wrong category. Yeah, this is never a good. I mean, this is simply doesn't apply. Yeah, the point is what you show. Yeah, and maybe I can do this here as an important remark. Really in red. For quantization, LMC algebras are not at all useful. And therefore, because, yeah, if your algebra, if you have an algebra A containing two elements, Q and P, with a canonical commutation relation, Q and P being IH bar 1, H bar not 0, then there is no submultiplicative seminorm on A beside. Well, 0 is always a seminorm and 0 is always submultiplicative, but that gives only the maximally non-Hausdorff topology. Yeah, that's a stupid seminorm. Yeah, so canonical commutation relations forbid LMC algebras. Full stop. Yeah, so we have never ever to think again about LMC algebras in the context of quantization. This simply is the wrong statement. Yeah, if we are interested in algebras containing elements satisfying such a commutation relation, we are out of the game with LMC algebras. Yeah, in particular, there are no Banach algebras, no C-star algebras, and whatsoever containing such elements. This is a statement you probably know. Yeah, but this has nothing to do with Banach. It's about submultiplicativity of a seminorm. Yeah. Okay, so so R equals 0 is sort of the boring thing. Yeah, let's switch back here. So what are other features I would like to explain? Yeah, we can determine the completion. Yeah, so that's maybe part 5, 6. Is it 5 or 6? Let's see. 6. Yeah. So what is the completion? And of course, SR of V. As a subspace inside. So how do we get the completion? We get it by putting a little hat on top, and but there's an explicit description. We can view it as a certain subspace of the Cartesian product where we have this summability property. So it consists of formal series of Vk, k equals 0 to infinity. So where Vk is an element in the completed k-fold projective tensor product. In finite dimensions, this is just a k-fold tensor product. Yeah, such that we have that the semi-norms is still defined, right? So that this quantity is finite for all P continuous semi-norm on V. Yeah. So this is sort of easy to guess. Yeah. We have two directions where we have to complete. Yeah. For a fixed tensor degree, we have to complete. That is taken care of by completing the tensor product. Yeah. And then we have to complete, and that's the interesting direction, if you want, in direction of the tensor degree. And in direction of the tensor degree, this is the summability summability of this series here, yeah, of this series. And now sort of the growth of these numbers have to compensate the growth of the factorial. That's the idea, how you complete finite sequences to L1 sequences or something like that. It's the same kind of argument here. Yeah. And in particular, this guy here that really converges in the TR topology. Oops. Then it converges even absolutely. Yeah. So this formal series in the Cartesian product. Yeah. So this is viewed as a subspace of the Cartesian product of all these completed guys here. There it really converges in the nice topology we cooked up. Yeah. So this is really sort of a converging Taylor expansion, if you want. Yeah? And the same thing for SR in here. The same with symmetric tensors. Yeah, so we have a good understanding what the completion looks like, how big it is. Yeah? And now, okay, we have to maybe find better models for it and better forms. But this is the completion, full stop. Yeah, and now we can try to study it. What happens in finite dimensions? How does this space look like? How does this look like? Maybe I should also write that the symmetric tensor product is also SR continuous. And so in fact, you get the same estimates. So if you take the symmetric tensor product of two symmetric tensors, you get an estimate like this. Sorry. No. Yeah. What's going on here? Where's my eraser? You get the same estimate here to PR of V to PR of W. And so I have to apologize, Martin. I'm using here the wrong convention for the symmetric tensor product. Yeah, the one with the factorials in the wrong position, just to get this estimate cleaner. Yeah, otherwise there would be some but there would be some little modifications. This makes it a bit easier. Yeah, so this is. Good question, and the answer is yes. I think so. Yeah, we did that actually for when we come to the Lie algebra situation. I think it's true. Yeah, yeah. Sorry, the question was whether the Hopf algebra structure. I mean, the tensor algebra and the symmetric algebra, they are also Hopf algebras. Yeah, they have a co-product, and turning them into bi-algebras, whether this is also continuous. And I would say yes. Yeah, I think this is true. Yeah, I think we even have claimed that in this paper I'm discussing this afternoon. I will look it up and then I can answer you this afternoon. But if I remember correctly, it is continuous. Yes. Mm-hmm. Yeah. So it's really yeah. Mm-hmm. Yes, it is continuous. Yeah. Okay, so that's the classical algebra in some sense. Yeah. So we have now nice little algebra, and so the little exercise, yeah, is described as R of V completed for, let's say, V being Rn, and so this is what you do, right? That okay. You will see that in the exercises this afternoon, and maybe I can give just a last little statement is the following. If and there are non-negative is important. So you take now an element, let's call it phi, in the topological dual. Yeah, so there are also two churches, right? The topological dual is either V prime or V star, and the algebraic dual is is the other way around. Yeah, well, there's of course only one church and heresy. Yeah, so this is the church. Yeah. Okay, so what can you do? You can evaluate an element in the symmetric algebra at V. Yeah, so this is a evaluation functional. You go back to complex numbers or real numbers. Yeah, and maybe I should also say that symmetric algebra, typically I'm interested in the complexification of the symmetric algebra. Yeah, so I forgot to write down always the C to do that. Yeah. Ah. Yeah. Okay. So anyway, so this is the character by evaluating at phi. Yeah. So that's it's uniquely defined by the property that here we get the evaluation. Yeah, and then you extend it to be a character. Yeah. And so this is continuous in the SR topology. Yeah. Therefore, extends to the completion, and therefore the elements of the completion can be viewed as functions, and in fact continuous functions on V star. Yeah, I can take an element in the completion, evaluate it at phi. This is delta phi of V. Yeah, so this is the way how you view them as functions. So elements in the completion, that they are not some arbitrary random funny sequences of tensors, but they have a very explicit interpretation as functions on the topological dual. Yeah. And now you can ask yourself the question, what kind of functions do we get? Yeah. There are certain functions, and we will get an answer in finite dimensions. There's a nice description of these functions, what you get. And this is, I guess, a very important statement, that this completion doesn't go out of control. Yeah, we are still talking about functions. Yeah, they are not polynomials. If you don't, if V is here in not in the completion, but just in the symmetric algebra, then this is a polynomial. Yeah, this is a polynomial function. But you get a bit more than polynomials, and now the question is which polynomials you get, and this is here what you do in this exercise. Yeah? Okay, but now, of course, the important question is the star product. Yeah, so I have yeah. Yeah, that was the reason why we started the whole business, right? So so let's do first, as warming up, the continuity of the Poisson bracket. Yeah, I mean, if the star product is continuous, and sort of has a nice Taylor expansion in H bar, then each term should be continuous as well, right? I mean, so let's start.
Stefan?
Yeah?
Yesterday you made the distinction between polynomials and the symmetric algebra.
Yes, yes.
And now you completed the symmetric algebra, right?
Yes.
Are the polynomials in this completion now? Or the continuous polynomials?
No. There's in finite dimensions,
they're the same.
It's the same thing, yeah. But in infinite dimensions, polynomials on the algebraic dual need not to be continuous. Yeah, I mean, if you would take continuous polynomials on the algebraic dual, I'm still not sure, and this might be in the completion because we completed here also the projective tensor product. Yeah, so if your polynomial on the algebraic dual is continuous enough, then they might be inside. Yeah, but here the completion goes in two directions. Yeah, so the k direction, if you want, that's the non-trivial one, giving you something like exponential functions. Then, yeah, so some transcendental functions, and on the other hand, I mean, nobody is interested in freaky polynomials on the algebraic duals which don't have nice enough continuous properties. Yeah, so maybe these are simply not interesting, I would say. Yeah, it's more the direction of the tensor degree which is important here, which I would like to complete and where I hope for gaining interesting stuff. Yeah.
Okay, thanks.
Okay. Yeah. Okay, so now let's try to do that. Yeah, and so what we do is the following: we take an element in the symmetric algebra, 2 copies of degree n and m, fixed degrees. Yeah, so it's a finite sum of factorizing tensors of these degrees. Let's say it's symmetric, and then we apply our operator p lambda to it. Yeah, we get, well, then we know that this p lambda of u will be an element. It lowers the degrees here by 1, and it lowers the degrees here by 1. Yeah, so now we want to estimate this. So what we have to do is, well, we have to use the tensor powers of n minus 1 and the tensor power of m minus 1 and apply it to this element, and we want to estimate that. Yeah, and this is in some sense very easy. You just have to spell out how many p's you have to distribute. Yeah, and what you get is you get a lot of pn plus m of u. Yeah. But then you sort of have to estimate one of the lambda of the factors. And because of the Leibniz rule, you get something like that. And I have, of course, assume that this thing is continuous with respect to p, should mean that I have, for this bilinear form, an estimate like that, P of V, P of W. Yeah? If this bilinear form is continuous, that means I find a seminorm, a continuous seminorm P such that this estimate holds. This is equivalent to continuity of lambda. Yeah? And then you just sort of look at this formula here, on factorizing tensors, and you prove it. And it's just a combinatorial game. And these two prefactors, they arise from Leibniz rule. Yeah, differentiating a polynomial of degree n and m gives you n times a polynomial of lower degrees, and so on. Yeah, that's where these factors come from. And they are bad. I put it to 1. I can do it. I can choose a different seminorm. I choose a seminorm such this. I mean, there would be a constant here. That would be continuity. And then I can sort of rescale my seminorm by this constant, and I get it to 1. This just for convenience that I don't get so many constants around. Yeah, I mean, these are so I see you're an educated Banach person. Yeah, that there you have to take care of these constants because you only have one norm. But I'm super lazy, and that's locally convex. The L stands for lazy, I guess. Yeah, that's very convenient that you have so many semi-norms around. Yeah, so you can sort of absorb all kind of numerical constants in a definition of a semi-norm. Yeah, that's the so without restriction. Yeah, we have a 1 here. Yeah, I mean, if there would be a 5, then I could rescale my semi-norm by 5, and then I would still have a continuous semi-norms, and I don't care about operator norm of lambda. Yeah, there's no such concept in locally convex topology because you have no distinguished norm, yeah, or semi-norms. Okay, so so this seems to be a good assumption here now that we have a continuous lambda, yeah, which hopefully gives us a continuous Poisson bracket. And now we have this estimate here. And now you see the whole problem of the star product already in this equation. Because if we now think of how the star product is built, we have to apply the P lambda over and over again. Yeah. And so applying it more and more and more produces more and more prefactors here. So in the end, we will get an n factorial and an m factorial. So we get a factorial growth of these numbers here in our estimate. Yeah? If we think of the exponential series. Yeah? The exponential series is nice because it also comes with an n factorial, but in the denominator. That's good, but there's still one too much. Yeah? There's one factorial of the exponential series in the denominator. That's the good one. That's our friend. And then we have 2 in the denominator. 1 cancels, but 1 is left. Yeah? And that is sort of the heuristics why we need to balance factorials. Yeah? And we have to balance factorial to the power 1. Yeah? And that already suggests that R equals 1/2 is good because we have 2 factors in the star product. Yeah? So each of them has to take care of a square root of a faculty to balance this, and then we get along. Yeah, so that's the heuristic argument how one cooks up these semi-norms, why this is clever and why R equal 1/2 should be the limiting case. Yeah, so R bigger would be even better. Yeah, then we balance easily. But R equal 1/2, that's sort of the way to go. Yeah, and that gives the biggest completion on the other hand. Yeah, I mean, if R grows, the completion gets larger, the conditions gets more severe. Yeah, the summability becomes more restrictive. Yeah, so from this simple estimate, and it's just a sort of a counting of number of terms by the Leibniz rule. It's nothing important, nothing mysterious going on here. Yeah, it's just that. Yeah. So from this observation, you can already sort of guess. Well, it's always easy to guess if you know the answer. Yeah. But you can try to guess the, why these semi-norms are sort of the good ones. Yeah. And okay. So now for the and because we have now all degrees around, yeah, not just fixed degrees. For fixed degrees, this operator P lambda is continuous. That's nice. Yeah? But we have a direct sum of all degrees, and then you see this guy cannot be estimated uniformly anymore. Yeah, this goes out of control if we do this estimate on a direct sum, unless we rescale our semi-norm here appropriately, and so that. For the Poisson bracket. So if we take now this guy, and we need R bigger than 0 here for that one, and we take the lambda Poisson bracket of 2 elements in here, then, well, we would get for each symmetric degree of V and W, we get this prefactor N and M. Yeah? But we can estimate N by 2 to the power of N. For sure, we can do that. Yeah, that's a good estimate. N is always smaller than 2 to the N. Yeah, yeah, this should work, right? So so what we get is that we rescale our semi-norm before doing our game here. Yeah, and then I need well, I taking care of the R was of course not correct. I should write down the correct formulas. Yeah, this is sorry. So the correct formula here is that we let's get this +1. That's the one we need here. So we take this one here and rescale the semi-norm appropriately, and then we get the continuity of the Poisson bracket. Yeah. So this is exactly this mechanism here. Where did I? This mechanism of getting here. If we rescale the semi-norm, we get additional powers here, and they will help to estimate the K and the N and M we have here, yeah, from the Poisson bracket. So this is nice. So if lambda is continuous. Yeah, so we have to invest this continuity of lambda, of course. And the continuity of lambda, that's always this nice little estimate here. Yeah, and we always take only those semi-norms which satisfy this this estimate here, and they still determine the topology, of course. Yeah? So that's good. Yeah, so that's all nice. And the point is, of course, now Poisson bracket is only the first term in the star product, and we have to do a whole exponential series of the thing, yeah, and of these p lambdas. And as I argued, now it's time for the theorem, if you want. That's the continuity of this star product. So suppose lambda is continuous and P is a continuous semi-norm satisfying our estimate. No, I want a pink one. So pink estimate. Yeah. Then what we get that we should write all the conditions here. That's the important one. Then we get the continuity of the star product. So if we take this A, B, then we get the following. We get some constant irrelevant one and another one where we have to rescale our semi-norm, and we rescale our semi-norm and then do this guy. So this is for all A and B in the symmetric algebra. Yeah. This is the estimate we have. Yeah. And so how do you prove that? Well, this is I have some 10 lines of estimates. It's not difficult at that stage anymore. Yeah, you just have to do a plug and play proof using the definition and unwinding everything. There's no big secret here anymore. Yeah, so I would prefer not to write down now one page of crazy formulas. You can find that, of course, in the paper. Yeah, but it's I think it's a good exercise to actually do that yourself, and I think maybe Michael does it in a one-dimensional case. Yeah, so where you see all the problems. Yeah, I mean where you see all the tricks. So we will do that as an exercise. Yeah, and the heuristics is really that we have to balance enough factorials. Yeah, that's why this R equal 1/2 comes about. Yeah? And so yeah, I think that's very nice. Yeah, and this R equal 1/2 is sort of sharp. Yeah, for smaller R, you definitely do not get continuity. Yeah, this is sharp. Yeah, I should write it here. Yeah. So this is the continuity of all these constant star products. Maybe I should now go a bit more. Once you have shown this continuity, you can of course ask the following question. I mean, now let's take really elements in the completion. So the star product extends by continuity, but it extends by continuity. That means if you have an element in the completion, you have to approximate it by elements in the symmetric algebra, both of them, and then you take star products of the approximations, and this converges to the star product. This is how extension by completion goes. But this is not what you want. You want the formula for the star product, and you want the formula to be correct. Yeah? So that means that the star product done by completion is equal to the following convergent series. Yeah? The series of the exponential function which you want to have. Yeah, so this is what did I write? IH bar to the k over k factorial, and then there was mu circle and this operator p lambda to the k acting on this guy. So this is the formula for the star product, is absolutely convergent. Yeah? Again, from now on, R is always bigger than 1/2. Yeah, bigger or equal to 1/2. I will not write it anytime again. Yeah, so this is so we really get the formula. Yeah, this is nice. Yeah, it's not this abstract extension by continuity. Yeah, but it's really the formula we had before stays valid as a convergent series. Yeah, this is an additional statement. Yeah, you know this kind of difficulty. Yeah, that if you think of the Fourier transform on Schwarz space. Yeah, you have a nice integral. Now you know it's isometric for the L2 inner product. So by abstract nonsense, it extends to L2 as a unitary. But does the formula with the integral stay valid? That's a much more tricky question, and in fact, you only know that it stays valid on certain points, and not on maybe not on a set of measure zero and so on. Yeah, so this is extending something by continuity is a quite abstract gadget, and you want more in many situations. Yeah, you want that formulas stay valid. Yeah, and this is true here. Yeah, and what you also see is that from this convergence here, you can now interpret that as a little bit different. You say, well, there are coefficients showing up here, depending on A and B, and then as our H bar is here, and that's a kind of a Taylor expansion in H bar now, and it converges absolutely. Yeah, absolute convergence with values in this funny locally convex space. So, as a consequence, the map taking H bar to, and I write now the H bar explicitly down here. Yeah, so this map with values in this big space here for all A and B, yeah, is entire. Yeah, with Taylor series given as above. Yeah, these are the Taylor coefficients here. Yeah, so this really converges as an vector-valued holomorphic function. Yeah, of the complex, if you want, variable H bar. Okay, we are maybe only interested in positive H bar, but never mind. Yeah, it's nice feature that this is really entire here. Hmm? And we have the Taylor expansion explicitly given. Hmm? And now, okay, we have these nice features, and maybe I just give a few more features which may or may not hold depending on whether the vector space V has these features. Yeah, so some more features depending on V. Yeah? And there's I think one is pretty important if you do it locally convex analysis. It's the question of nuclearity. Yeah, so I don't want to go into details. I just want to mention it. There are again two churches in locally convex analysis. One says everything is about nuclearity, and the other church says nuclearity is a completely irrelevant concept. Yeah, so I don't know, but the theorem is the following. We have the following statements. V is nuclear, SR of V is nuclear. Well, and you can add a third one. You can have also the tensor algebra is nuclear. So this is equivalent. Yeah. So nuclearity is inherited. Yeah. And nuclearity is in one way to view it is I think that was Grothendieck's original motivation. The nuclear spaces, they are sort of finite dimensional. Yeah. They behave like finite dimensional spaces in many aspects, even though they are not. Yeah. And this is finite dimensional spaces, they are nuclear. Yeah. So starting with finite dimensions, then of course this star product algebra is not finite dimensional anymore, but it stays nuclear. Yeah. And nuclear has many nice applications. So you have an abstract kernel theorem. I guess that's the most important one, but you have also other nice features. So the ambiguity in choosing the tensor product. Yeah, okay, there was in Kasia. Yeah, that's for her is important that you have this ambiguity in choosing what kind of tensor product you want to take. That doesn't really matter. Yeah, for nuclear spaces. Yeah, many tensor products, the injective and the projective, and sort of a whole bunch in between, they simply coincide. Yeah, that's an important point for Kasia, and not only for her, yeah, I guess for many people, yeah. And so we get a nuclear star product algebra here, yeah. That's all nice, and maybe I should also say that and then I will stop, yeah. That we have good functorial properties for continuous linear maps preserving the bilinear form we started with, of course. Yeah. So they will extend to continuous algebra homomorphisms of the star product. Yeah, so that's not very surprising. I mean, the way we built it, it was sort of functorial from the beginning. Yeah, so that is nice. And well, okay, I could tell you something more about the Schauder spaces, but that's not so important, I guess. This is of course important here for symmetries. Mm-hmm. Yeah, so symmetries are those linear maps preserving lambda. Yeah, and that's and in fact even affine maps extend. Yeah. Okay, so I think that's maybe enough for this morning, and this afternoon I will give you some examples of this construction, and then we go on beyond the linear case to the constant case to the next complicated, and that will be linear Poisson structures this afternoon. Okay, thank you.
Thank you very much for your talk. Are there any questions?
Too much analysis.
you.
All right. It doesn't seem to be the case. Then we can thank our speaker again.
So one question.
No, sorry. Yeah.
It's a very deep question. So I guess the spaces S hat R and T hat R are not metrizable. So when you speak about continuity, do we mean like sequential continuity or
no,
continuity?
I speak about continuity. They might not be first countable, so it's not. It may not be Fréchet. So continuity is a different thing than sequential continuity.
Yeah,
and it's also not separate continuity. It's really continuity what I'm talking about. The price is, of course, the price is that our lambda is continuous. Yeah. That's a non-trivial price in infinite dimensions. In finite dimensions, it's no price at all. I mean, every bilinear map is continuous. But in infinite dimension, I should have stressed this. I really require this bilinear map to be continuous and not separately continuous. The whole game only works there. I have no idea what about separate continuity or only sequential continuity. Then this is much more complicated and delicate. I would invite anyone to try. So this is not so easy, I think. This is a price. This is a non-trivial price to pay in infinite dimensions. I will give an example this afternoon where this is true, but many interesting situations are not captured. That's the bad news, if you want. So okay.
Yeah, thanks.
Martin, hinter dir.
Just, I don't know whether this is a spoiler. So what about exponentials or even Gaussians?
This is of course spoiler. No. Where did I argue here? So our R is at least 1/2. And the spoiler is that Michael will exactly determine function classes where you interpret these elements in the completion now as functions on the dual, and then you can ask about if they are exponential or not, and you have a very, very precise understanding. And unfortunately, the Gaussian is not in there. The Gaussian
Thanks.
not, and I don't tell anything more now, but some other interesting functions will be in there. So the Gaussian not. That's also in some sense known. That there was a paper by this Japanese group of Omori, Maeda, Yoshioka. They computed star products, Wick star products on a more heuristic level for Gaussians and trying to make sense out of the series directly, and then they observed a failure of associativity. So that was I mean you can sort of try to make sense out of formulas, but then you lose associativity, or you say, well, it's not continuous, it doesn't extend, and Gaussians are not in the completion. Okay.
Okay, are there more questions or comments?
No, there's nothing in the chat anymore.
No.
Chen-Chang? There's one more question.
All right.
There's a question here, just a second.
Hello.
Just
Hi.
Yeah, it
Okay.
works like that. I think.
So I'm just wondering. So the whole thing now you're trying to get this somehow a topology on this function space, right?
Yeah.
So
Mhm.
so make the aim to make everything like continuous and but not just formal power series.
Yes. Mhm.
Is it your aim at some sort of C-star algebra so that you can build up the representation in the classical way of Hilbert spaces, and that's the.
Yeah, let me perhaps repeat. I don't know if everybody heard. I mean, the question was whether I'm aiming at C-star algebras in order to do representation theory and things like that. C-star algebras are nice. I would love to have them. I'm doing something intermediate, I would say. And the problem is if I have such commutation relations, there's no hope for C-star algebras. Yeah, not even LMC. Yeah, LMC is much more general than C-star, and that's excluded already. Yeah, so what people do usually is say, well, Q and P, nobody is interested in Q and P. Let's take exponentiated versions and then do a little bit heuristic of these Weil commutation relations, and then you get the C-star Weil commutation relations, and then there is a nice C-star algebra where this all works. That's true for the constant Poisson structures, but not beyond. Yeah. So the point is, the logic here is a little bit, I would like to treat these examples, which you can also treat in a different way. Yeah. I would like to treat them without the knowledge of that there are some nice integral formulas around and things like that. I would like to try to develop techniques, yeah, to just work with the formal power series. Yeah, that this is sort of the handicap I give myself. Yeah, so because this is the thing which we have in general, yeah, in full generality. Yeah, these formal power series, and the idea is, are there possibly scenarios, techniques where this is enough to cook up some analytic context? Yeah, so I'm much more modest. Yeah? I mean, these algebras which we get here in the end, I mean, they are of course not C-star algebras. They are, if you start with something finite dimensional, it stays first countable. So this will be a Frechet algebra. That's all nice. Yeah? And then with locally convex algebras, you can very well do representation theory on Hilbert spaces. But the price is that typically some elements might become unbounded operators. Well, not too bad. Here, there are experts here in the audience. Matthias knows all about that kind of stuff. Yeah. So you can handle that. It becomes much more involved, but there is technology available. Yeah. And in the end, once you represent it on a Hilbert space and you have sufficiently nice self-adjoint operators found, then you have the spectral projections and you can cook up a C-star algebra affiliated one. Yeah. And then sort of you're back to the usual things. Yeah. But the point is, I want to start with something which is always there. That's the formal star product. There we have good general existence. Yeah. And I would like to try to train myself using only that. Yeah. And at the moment, I mean, I can handle constant Poisson structures, not too much. Yeah, I admit. Yeah. But there will be some more this afternoon. Yeah. So linear ones, still not too much. Yeah. So this. Yeah. Does that answer the question? Yeah.
That's
okay.
Great.
Thank
you.
Good.
All right. So I think we can thank our speaker again. And we'll now have just a short break to switch to the next speaker.